SwayamPrabha. Digital India. Educated India.
In this lecture, we will be studying the transient response of PD control system. In this direction, we will be finding the expression of rise time, settling time, peak time, and maximum overshoot. And these parameters can be used to modify the transient response of the system. If you would like to reach the desired values very fast with less magnitude in overshoot and undershoot, how we can use this parameter to modify the response. Then we will conclude the lecture. In the last lecture, we discussed about the specification and how we can define this specification in the response plot. In this lecture, we'll be finding the expression of this specification in time domain. We'll start with finding the rise time. Rise time. As per the definition, the rise time is the time taken to first reach the final value. So from the step response, let me define this the figure 1. From the step response, in figure 1, we see that at t equal to tr, the output is y of t equal to 1. Hence, if you remember the equation we had, let me write the equation. Here, we had y of t equal to 1 minus e to the power zeta omega n t into cos omega dt plus zeta omega n by omega d and sine omega dt. So this is the expression we found. And if you substitute y equal to 1, let me write the equation number 1. In equation number 1, we can write cos omega d tr plus zeta omega n by omega d sine omega d tr equal to 0. After rearranging yields, we can write tan omega d tr equal to omega d divided by zeta omega n, or we can write in place of omega d, you can write omega n 1 minus zeta squared divided by omega n zeta. For the underdamped system, as we have discussed before, for the underdamped system, the pole locations as following. Let me write the poles for the underdamped system. We had S12, 2 poles, minus zeta omega n plus minus j omega n root over 1 minus zeta square. And this is we denoted by omega d, or we can write zeta omega n plus minus j omega d. And if you plot these folds in the S plane, we can have something. This is the minus zeta omega n, and here we have omega d, and here we have another minus omega d. So now, and this is basically the one of the complex conjugate poles. And if you this is if you denote by beta, and this is obvious from the expression we can write omega d t with angle. This is basically RAS, and this is the IMS, imaginary axis. And from this plot, we can write omega d tr equal to pi minus beta. Or from this we can write tr equal to pi minus beta divided by omega d. If you multiply 10 or 10 pi minus beta, we can write, because already we are having omega here, if you look, omega d are equal to this expression. So from this expression and this expression, we can write minus 1 minus zeta squared divided by zeta. Or we can write minus tan beta equal to minus 1 minus zeta square divided by zeta. And from this we can write beta equal to tan minus inverse and 1 minus zeta square by zeta. So this is the expression for beta, and if you can find beta here, we can find tr. So this beta can be used to find the tr expression, because this is the tr expression. So here omega d is known and beta is unknown. So if you can find beta from this expression, we can find tr. So if you notice carefully here, this beta is the function of zeta. And zeta also depends on the control parameters, what you have defined. We have defined some expression zeta, some expression kp, kd, and omega in some expression kp, kd, if you remember. So using these control variables, we can modify the zeta. And if we can modify zeta, also beta will be modified. And based on beta, we can modify. So this is how we can improve the rise time. So now let's go to our second specification, peak time. In peak time, the definition was the peak time occurs at the first time when dy dt is 0. So of course, obvious, this is from the plot. At Tp, here the value is constant. So we can write at Tp, at t equal to Tp, you can write dy dt equal to 0. So for this, we will take the time derivative of the equation number 1. Let's move. Dy taking time derivative of equation 1, else we can write dy dt equal to zeta omega n e to the power minus zeta omega n t cos omega dt plus zeta omega n divided by omega d sine omega dt minus e to the power minus theta omega n t into minus omega d sine omega dt plus theta omega n by omega d cos omega dt. And after rearranging this expression yields e to the power minus theta omega n t sine omega dt zeta squared omega squared divided by omega d plus omega d. So this is how we can write the expression. Now from this we can write let me write the equation number 2. From equation 2 we can write the peak time t equal to Tp, we must have sine. So this part, if it is 0, then this sine omega d t equal must be 0. And under this condition, we can write omega d Tp. Here t equal to Tp, you can write this condition, and equal to 0, pi, 2 pi, like this. And clearly, from this, the first peak correspond to omega d Tp equal to pi. And from this expression, Tp equal to pi by omega d. So this is the expression for peak time. So here again, you can see that omega d, basically, we can write omega n root over 1 minus zeta squared. So here omega n and zeta are differential control parameters. So we can modify the omega d, and also you can modify the peak time. Now let's go to find the maximum overshoot. The next specification, maximum overshoot, which is denoted by MP. The maximum overshoot occurs at the peak time t equal to Tp. That is obvious. It is already we have done. The maximum overshoot occurs t equal to Tp. So based on this definition, we can write the maximum overshoot occurs at the peak time t equal to Tp with the maximum response. We can write Yp at t equal to Tp. If you denote Yp is the maximum response, 1 minus e to the power minus zeta omega n t cos omega d Tp plus zeta omega n by omega d and sine omega d Tp. Here also Tp. And from this, okay, also we know that from the previous specification for peak time, omega d Tp equal to pi. So from this, such that cos omega d Tp should be equal to 1, sorry, minus 1, because omega d Tp equal to pi, and sine omega d Tp equal to be 0. So therefore, we can write, therefore, the maximum response yp equal to 1 plus, if you substitute these x values in the previous this expression, we have 1 plus e to the minus pi zeta omega n by omega d, or we can write 1 plus, in place of omega d, if you write the expression for omega n root over 1 minus theta squared, so our expression yields to be pi zeta divided by 1 minus theta squared. So this is the expression, and since we are using the state command, so we can write the maximum percentage overshoot of the final value we can define as MP equal to yp minus 1 by 1 into 100%. And from this we can write e to the power minus pi zeta root over 1 minus theta square into 100%. So this is how we define the maximum overshoot of the response. Similarly to the previous specification, here also we can modify the maximum overshoot using the zeta, and zeta also depend on control parameters. This is how we do the modification. Now we'll go to our last specification, settling time. Yes. Settling time, as you know, that it is basically the difference between the current and final value. And we had response something, maybe something like this. So this is basically, we can say the difference between the, this is the basic idea, we can say current angle of the aircraft, we can say, because the equation we are getting are the kind of the mathematical things we are doing based on the aircraft systems, attitude motions. So now the settling time, we can write here the difference between current and final value of y of t. So we can write y of t minus 1, we can write minus e to the power zeta omega nt cos omega dt plus zeta omega n divided by omega d sine omega dt. So this is, we are getting this expression from the equation 1. This is straightforward. Further, we can write this expression as e to the power minus zeta omega n t cos omega dt plus zeta omega n root over 1 minus zeta square and sine omega dt. In place of omega d, we wrote this omega n root over 1 minus zeta square. And further, we can write minus e to the power minus zeta omega n t, and if you 1 minus zeta squared. If we take common, then we can write cos omega dt sine beta plus cos beta sine omega dt. How you substitute cos beta and sine beta? Because you already know, since you know tan beta equal to 1 minus zeta squared by zeta. And from this, we can write cos beta equal to zeta and sine beta equal to over 1 minus zeta squared. So we substitute these terms in this expression. Since we are having yt minus 1, where final expression we can write it minus e to the power zeta omega and t root over 1 minus zeta squared. And from the sine a plus b, if you remember, we can write from this expression sine omega dt plus beta. The magnitude of this value is basically always lies between 0 and 1, or I can write, since we know that the magnitude of sine omega dt plus beta is always less than 1, less than equal to 1. Expression we can write. So if you use this expression in equation, let me write this is equation number 2, equation number 2. And if you use this condition in equation number 2, we can write yt minus 1 if we take the magnitude of this, and we can write less than equal to e to the power minus zeta omega and t divided by 1 minus zeta squared, because this the magnitude of this is less than equal to 1, so only this, the first term will be there, and hence we can write the percentage deviation from the final value. We can write yt minus 1 by 1, we can write in 100% less than 2%. So 2% we have assumed while we are defining the response, all this stuff. So 2% we can tolerate in the response. Suppose this is the difference between 2%, between the current and final value. So we can write this expression, or we can write, but in some books they are having different values. So if it is different, we can calculate accordingly for TS. So e to the power minus zeta omega and t 1 minus theta square less than 0.2 we can write. And from this we can write Ts equal to natural logarithm 0.021 minus zeta square divided by minus zeta omega. So this is the expression for settling time. So if you notice here, again, the settling time also depend on the natural frequency and damping ratio. So using the control, we can modify the settling time, how fast. If you want to reach the, if your aircraft needs to be reached to the final value very quickly, then you can, using the control, you can modify the settling time. So this is how we do the, analyze the system using the controls. Let me write one note here. This maybe you will be using some places will be using, this is also important. For damping ratio, between 0.1 and 0.9. So this is basically standard value generally we consider for the control system design, this range. The quantity we can write 0.02 1 minus zeta square varies between 3.9 and 4.8. So this is, let me write the expression, for example, equation number 3, and we may approximate the expression for Ts by Ts 4.4 divided by zeta omega n. So sometime we use this value for the underdone system. And yeah, this is also for the designing control, we use this expression also. So let's stop it here. We'll continue from the next lecture. We'll have some examples how we can design a controller for an aircraft attitude systems. Thank you.